In the deep silence before time, long before the spiral arms of our galaxy swept through the darkness, before the sun burned or the earth spun, primordial clouds gathered in the ancient night. These were not the gentle nebulae we now see drifting luminous in telescopic images, but vast chaotic seas of gas, raw and unshaped, filling the young universe's void. Their temperatures seethed, their velocities raged. In this era, the universe was young, but already in turmoil, a place where the orchestra of physics played a wild, discordant symphony, and the notes of gravity, hydrodynamics, and thermodynamics intertwined in a violent dance. It is here, in the earliest epochs, that we look for the origins of stars, not solitary, stately beacons, but clusters born in tumult, midwifed by forces so titanic that their echoes still ripple through the cosmos. Here, turbulence, not the gentle rippling of a tranquil sea, but the fury of supersonic gales, became the architect, the sculptor, the destroyer, and creator alike. The primordial turbulence was not an incidental feature. It was the very crucible that determined the fate of the universe's first clouds, fragmenting them, shaping the seeds of future suns. The concept of turbulence, familiar to anyone who has felt the judder of an airplane wing, takes on epic proportions in the context of the cosmos. In the interstellar medium, where densities are measured in particles per cubic centimeter, turbulence is not a mere inconvenience, but the governing law. When clouds of hydrogen and helium, infused with traces of lithium and deuterium from the Big Bang, began to coalesce under gravity, they did not do so in peace. Instead, they roiled with energy, velocity fields crossing and colliding, shock fronts compressing and rarefying matter, all at speeds exceeding the local sound velocity. Supersonic turbulence. The very phrase evokes images of shock waves tearing through matter, of regions compressed into filaments and sheets, while others are left void and rarefied. In the context of primordial star formation, this turbulence was born from cosmological flows, driven by gravitational collapse, amplified by the infall of dark matter halos, sharpened by the cooling of gas as it radiated away its energy. The result, clouds that could fragment, break apart, and seed many stars where perhaps only one massive sun might have arisen in silence. To understand the significance of this process, we must travel backward in time, 13.8 billion years, into the heart of the cosmic dark ages. After the Big Bang's afterglow faded and the first atoms formed, the universe was a cold, dark place. Clouds of gas, nearly uniform but with subtle ripples, quantum fluctuations stretched to cosmic scale, began to collapse. These ripples, captured in the cosmic microwave background, are the fingerprints of the universe's first structures, but gravity alone cannot account for the fractal complexity we now see, the filaments, knots, and clusters of galaxies. Turbulence, then, emerges as a necessary ingredient, and not just any turbulence but supersonic turbulence, where velocities surpass the speed of sound in the medium, Mach numbers of 10 or greater. Theorists like Chris McKee and Richard Klein, in the late 20th century, first modeled the interplay of turbulence and gravity in molecular clouds, showing how such motions could both support clouds against collapse and simultaneously induce local compressions dense enough to trigger star formation. Their three-dimensional hydrodynamic simulations, pioneering for their era, revealed a universe where chaos begets structure. But in the primordial universe, things were different still. The lack of metals, elements heavier than helium, meant that cooling was inefficient. Gas could not radiate away heat as effectively, so temperatures remained high, sound speeds fast, and turbulence correspondingly more intense. The interplay of cooling and turbulence determined whether a cloud would collapse into a single massive object, a so-called population 3 star, perhaps hundreds of times the mass of our sun, or fragment into a swarm of lesser lights. Here, the mathematics of turbulence becomes crucial. In ordinary subsonic turbulence, as first described by Andrei Kolmogorov in the 1940s, energy cascades from large to small scales, obeying a precise power law. But supersonic turbulence breaks this serenity, introducing shocks, discontinuities, and density contrasts spanning orders of magnitude. The Mach number, a measure of speed relative to sound, becomes the decisive parameter. In a cloud with a Mach number of 20, for instance, Density contrasts can reach factors of 1,000, enough to locally tip the balance toward gravitational collapse, even as the cloud as a whole resists. The first hints that such processes might dominate the early universe came from increasingly sophisticated simulations in the 2000s and 2010s. Tom Abel, Greg Bryan, and Mike Norman, using adaptive mesh refinement codes, traced the collapse of primordial clouds within dark matter halos. Their results revealed the emergence of dense filamentary structures, signatures of turbulent fragmentation, within what had previously been envisioned as smooth, monolithic clouds. These filaments, compressed by supersonic flows, became the cradles of the universe's first stars. Yet the story of fragmentation is not just one of physical forces, but also of cosmic consequences. The number and mass of the first stars set the stage for everything that followed. Massive stars lived fast and died young, exploding as supernovae, seeding the cosmos with the first heavy elements, and perhaps even giving rise to the first black holes. Smaller stars, by contrast, could linger, their light red and dim, but persistent, potentially surviving to the present day as relics of cosmic dawn. To explore these themes requires diving deeper into the physics of turbulence and fragmentation. The interplay of gravity, pressure, and velocity fields is governed by the equations of fluid dynamics, specifically the Navier-Stokes equations, augmented by terms for gravity and cooling. In the regime of high Mach numbers, analytic solutions prove elusive, so scientists turn to simulations. Billions of computational cells, each tracking the evolution of density, velocity, temperature, and chemical composition. One landmark study, conducted by Volker Bromm, Paolo Coppi, and Richard Larson in 1999, used smoothed particle hydrodynamics to model the collapse of primordial gas. They found that, in the absence of metals, clouds could cool only via molecular hydrogen, which formed inefficiently through rare three-body interactions. As a result, the minimum fragment mass, the so-called Jeans mass, remained high, favoring the formation of massive stars. But as soon as turbulence reached supersonic levels, density fluctuations became so extreme that even low-mass fragments could condense, provided local cooling sufficed. Observational evidence for this primordial fragmentation remains elusive, but hints abound. The most metal-poor stars discovered in the galactic halo bear the chemical fingerprints of a generation of progenitors, some massive, some less so. Their abundance patterns, measured by astronomers like Anna Friebel and Timothy Beers, suggest that the first stars did not form in isolation, but in clusters, each fragment birthed from a turbulent parent cloud. The analogy to earthly turbulence is imperfect but evocative. On Earth, turbulence in the atmosphere and oceans shapes weather, mixes nutrients, and sculpts clouds. In the interstellar medium, turbulence is the weather, except the scale is measured in parsecs, the energies in supernova equivalents, the time scales in millions of years. Just as a thunderstorm can break a warm front into swirling vortices and isolated downpours, so too does cosmic turbulence fragment a cloud into the seeds of countless stars. Supersonic turbulence, however, is a double-edged sword. It both resists and enables collapse. On large scales, turbulent motions can support a cloud against gravity, like a swarm of bees, their collective motion keeping the hive aloft. On smaller scales, the same turbulence creates pockets of extreme density, where gravity can gain the upper hand. This duality lies at the heart of the so-called turbulent fragmentation paradigm, a framework that now underpins much of modern star formation theory. One illustrative case comes from the simulation work of Matthew Turk and colleagues in 2009, who modeled the formation of the first stars within cosmological volumes. Their results showed that as gas accreted into dark matter halos, it developed supersonic motions driving shocks into the cloud. These shocks compressed the gas into sheets and filaments, within which gravitational fragmentation could proceed. The result? Clusters of protostars, each forming within its own dense cocoon, rather than a lone behemoth dominating the scene. This insight marked a shift from the earlier monolithic collapse picture to one of multiplicity and complexity. It also shed light on the likely masses of the first stars, a question of profound importance. Massive stars produce copious ultraviolet radiation, ionizing the universe and ending the cosmic dark ages. Their supernovae forge the first heavy elements, while their remnants may seed the formation of supermassive black holes. But if fragmentation is efficient, a spectrum of masses results, with implications for the chemical and radiative evolution of subsequent generations. The physics of supersonic turbulence is not limited to the early universe. Even today, in the molecular clouds of the Milky Way, Mach numbers of 5 to 20 are common. Star-forming regions like the Orion Nebula, as mapped by Alma and Herschel, display a web of filaments and clumps, their kinematics betraying the fingerprints of turbulent fragmentation. The same physical laws apply, though the details differ. Cooling is now aided by dust and metals, and magnetic fields play a larger role. Magnetic fields indeed add another layer of complexity. In the early universe, their origins are debated. Were they seeded by primordial processes, or generated later by dynamo action? Regardless, even weak fields can channel turbulence, shaping the morphology of fragmentation. Studies by Ralph Klesson and colleagues have shown that magnetized supersonic turbulence produces a more filamentary, hierarchical structure, echoing the fractal patterns seen in clouds from Orion to Perseus. Beyond the realm of simulations and theory, the search for observational signatures of primordial fragmentation continues. One approach, championed by Anna Friebel and collaborators, is the hunt for extremely metal-poor stars, so-called stellar fossils. These ancient stars, with iron abundances less than 1/10,000th that of the Sun, retain in their atmospheres the nucleosynthetic imprint of the first supernovae. Their existence suggests that low-mass stars could indeed form in the early universe, an outcome made possible by turbulent fragmentation. Another line of evidence comes from the cosmic infrared background, measured by missions like COBE and Spitzer. Fluctuations in this diffuse glow may trace the clustering of the first star-forming regions, their spatial scale set by the interplay of turbulence and gravity. Theoretical models, such as those by Naoki Yoshida and colleagues, predict that if fragmentation was efficient, the resulting population of early stars would be numerous, their collective light detectable even across cosmic time. The study of primordial turbulence and fragmentation is thus a pursuit at the intersection of theory, simulation, and observation. It is a tale of physics writ large, a cosmic laboratory where the laws of hydrodynamics, thermodynamics, and gravity are tested at extremes inaccessible on Earth. It is also a story rich in philosophical resonance, for it speaks to the origin of complexity from chaos, the emergence of structure from randomness, the birth of light from darkness. This narrative, however, is not merely one of stars and clouds, but of the fundamental processes that govern the evolution of the universe. The fragmentation of primordial clouds set the initial conditions for galaxy formation, black hole growth, and the cosmic cycle of matter. It determined when and where the first light would shine, how quickly the universe would be enriched with heavy elements, and what sorts of planets and life might eventually arise. Supersonic turbulence, then, is more than a physical phenomenon. It is a metaphor for the creative potential inherent in chaos. Just as a storm can sculpt landscapes, so too can turbulent flows carve the universe's structure, seeding the diversity from which all future complexity emerges. The study of these processes is thus both a scientific and a poetic quest, a search for the origins of order, meaning, and beauty in the cosmos. The journey to unravel these mysteries continues. New generations of telescopes, James Webb, the Square Kilometer Array, the 30-meter telescope, promise to peer ever deeper, to catch the first glimmers of starlight, to resolve the structure of primordial clouds with unprecedented fidelity. On the simulation front, exascale computing enables ever more detailed models, capturing the interplay of turbulence, cooling, chemistry, and radiation across vast dynamic ranges. Yet each discovery brings new questions. What is the precise spectrum of masses for the first stars? How does turbulence interact with nascent magnetic fields? Can we detect the remnants of primordial fragmentation in the present-day universe? These questions drive the field forward, inspiring ever more ingenious experiments, observations, and theories. The story of supersonic turbulence fragmenting primordial clouds is thus a microcosm of the scientific endeavor itself, a process of breaking apart the undifferentiated darkness, seeking the seeds of understanding, piecing together the fragments into a coherent whole. It is a narrative that echoes across scales, from the smallest eddy in a laboratory fluid to the largest structures in the universe. In this light, the study of turbulence becomes not just a technical challenge, but a philosophical meditation on the nature of order and chaos, of structure and randomness, of the interplay between law and chance. It is a reminder that the universe's greatest beauty often arises not from symmetry and simplicity, but from the intricate, unpredictable patterns woven by turbulence. As we contemplate these themes, we return to the primordial clouds, drifting in the ancient darkness. We imagine their internal motions, a ceaseless, unseen ballet of gas and dust, of shock waves and rarefactions, of fragments forming and dissolving. We see in their patterns the seeds of future galaxies, the ancestors of suns and worlds, the distant echoes of our own origins. The fragmentation of these clouds, driven by supersonic turbulence, is thus both a specific astrophysical process and a universal metaphor, a testament to the generative power of chaos. From the formless void, structure emerges. From the roar of turbulence, the silence of stars. In studying these processes, we draw closer not only to understanding the cosmos, but to grasping our own place within it, a place shaped, in the deepest sense, by the interplay of order and disorder, of turbulence and tranquility, of fragmentation and unity. The journey is far from over. Each new observation, each new simulation, peels back another layer of the cosmic onion, revealing ever more subtle interactions, ever more intricate patterns. The field is alive with debate. Did the first stars form in isolation or in clusters? How efficient was fragmentation, and what determined the characteristic mass scale? How did feedback from the first stars, radiation, winds, supernovae, reshape the turbulent landscape, perhaps triggering or quenching further star formation? To answer these questions, astrophysicists draw upon an arsenal of tools: radiative transfer codes, magneto-hydrodynamics, chemistry networks, machine learning algorithms trained on terabytes of simulated data. Each approach brings its own insights, its own limitations, yet together, they converge on a picture in which supersonic turbulence is not a peripheral detail, but a central player, a force as fundamental to cosmic evolution as gravity itself. The interplay of turbulence and gravity produces a fractal hierarchy of structure, a cosmic web of filaments, sheets, and knots, spanning scales from light years to megaparsecs. Within this web, clouds fragment, stars ignite, galaxies assemble. The patterns seen in the distribution of galaxies today, the filaments and voids mapped by surveys like the Sloan Digital Sky Survey, are echoes of the same turbulent processes that shaped the first clouds. In the last decade, a new generation of simulations, so-called zoom-in cosmological models, have begun to capture the full range of scales involved, from the collapse of a single star-forming core to the assembly of a galaxy. Pioneering work by John Wise, Brian O'Shea, and others has shown how turbulence, seeded by cosmological accretion and amplified by feedback, can drive fragmentation across scales, producing a spectrum of structures reminiscent of those seen in observations. These simulations reveal a universe in which no scale is privileged, in which structure emerges hierarchically, in which the interplay of turbulence and gravity sculpts the architecture of the cosmos. Within this framework, the fragmentation of primordial clouds is not a one-time event, but an ongoing process, a cosmic cycle of creation and destruction, of assembly and dispersal, of unity and fragmentation. From the perspective of chemical evolution, the efficiency of fragmentation determines the timing and extent of metal enrichment. If massive stars dominate, their short lifespans mean rapid enrichment, but only in localized regions. If fragmentation produces many low-mass stars, metals are sequestered, and enrichment proceeds more slowly. This balance shapes the subsequent generations of stars, the formation of planets, and ultimately the emergence of life. Observationally, the search for the first stars, the so-called population 3 stars, remains one of the great quests of contemporary astronomy. Despite decades of searching, no unambiguous example has yet been found. However, indirect evidence abounds. The most metal-poor stars in the Milky Way, with iron abundances 1,000,000 times lower than the Sun, preserve in their atmospheres the nucleosynthetic fingerprints of the first supernovae. Their abundance patterns, as catalogued by the Saga database, suggest that the first stars were not all massive, but included a spectrum of masses, consistent with efficient, turbulent fragmentation. Looking forward, the next generation of telescopes promises to push the frontier back to cosmic dawn. The James Webb Space Telescope, with its infrared sensitivity, is poised to detect the light of the first galaxies, whose spectra may bear the imprint of population 3 stars. The Vera C. Rubin Observatory, with its wide-field surveys, will map the distribution of the most ancient stars, tracing the fossil record of early fragmentation. At the same time, laboratory astrophysics provides new constraints on the microphysics of cooling, chemistry, and turbulence. Experiments with ultra-cold gases, high-energy lasers, and plasma devices reproduce some of the key processes at work in primordial clouds, offering insights into the interplay of turbulence and fragmentation under controlled conditions. The synthesis of these diverse approaches, observation, simulation, experiment theory, constitutes the modern science of star formation. It is an enterprise marked by collaboration, competition, and a shared sense of wonder at the complexity of the cosmos. Each new result, each new model adds another brushstroke to the evolving portrait of cosmic evolution. Yet even as we uncover the mechanisms by which supersonic turbulence fragments primordial clouds, deeper mysteries remain. What is the origin of turbulence itself? Is it seeded by quantum fluctuations, amplified by gravitational collapse, or driven by feedback from the first stars? How universal are the patterns of fragmentation? Do they repeat in every galaxy, or are they contingent on local conditions? These questions touch on the deepest themes of cosmology: the origin of structure, the emergence of complexity, the interplay of chance and necessity. They remind us that the universe is not a static backdrop, but a dynamic, evolving system, shaped by forces both predictable and chaotic. In reflecting on these themes, we come to appreciate the profound unity of physics. The same equations that describe the flow of air over a wing or water in a river govern the motions of gas in a primordial cloud. The same principles of thermodynamics, of energy conservation and dissipation, apply equally to the birth of a star and the boiling of a kettle. In this sense, the study of turbulence is a bridge, linking the familiar to the cosmic, the everyday to the eternal. The narrative of supersonic turbulence fragmenting star-forming clouds is thus both a technical story and a philosophical meditation. It is a story of forces unleashed, of chaos harnessed, of order emerging from disorder. It is a story that has shaped the universe, and in a sense shaped us, for the atoms in our bodies were forged in stars whose birth was orchestrated by these very processes. As we gaze into the night sky, we see the legacy of this turbulence, a tapestry of stars and galaxies, filaments and voids, each a testament to the creative power of chaos. We see in the patterns of starlight the echoes of ancient storms, the fingerprints of fragmentation, the birth cries of suns. In the end, the study of supersonic turbulence in primordial clouds is a study of origins, of stars, of galaxies, of elements, of complexity, of life itself. It is a reminder that from the wildest disorder can arise the greatest beauty, that from the deepest chaos can emerge the most intricate order. It is a lesson written in the fabric of the cosmos and in the fabric of our own being. And so the story continues. New observations, new simulations, new theories will refine our understanding, revealing ever more subtle interplay between turbulence, gravity, cooling, and feedback. The cosmic dance of fragmentation and unity will unfold in ever greater detail, each step bringing us closer to a full understanding of our origins. But even as we approach this understanding, the mystery deepens, for every answer yields new questions, every discovery opens new horizons. The universe, in its boundless complexity, remains always one step ahead, a source of wonder, of inquiry, of inspiration. In contemplating the fragmentation of primordial clouds by supersonic turbulence, we glimpse the profound truth that underlies all of science. The universe is not a finished work, but an unfolding story, a story in which chaos and order, destruction and creation, fragmentation and unity are inseparable partners. It is a story that began in the darkness, with clouds torn by storms, and continues in the light of every star. And in that light, we find our own story reflected, a story of origins, of search, of understanding, a story shaped, in the deepest sense, by the wild, creative and generative power of cosmic turbulence.